Printed e-textiles are a category of e-textiles that incorporate electronics in textiles by printing. However, it is possible for the printed electronics to impact the wearability of the resulting e-textile. More importantly, the textile structure can influence the thickness of the printed film. My name is Abiodun Komolafe, and I will be discussing how the wearability of printed e-textiles can be improved by controlling the textile structure. First, I will give a brief overview of e-textiles and their applications, the integration technologies that currently enable e-textiles. Then I'll focus on printed integration of e-textile. What do we mean by the interface layer? How does the reduction of the interface layer thickness affect reliability? And the effect of the interface layer on the surface roughness. And I'll make some conclusions. The combination of textiles and electronics into a single device is what we call e-textiles. This technology or integration promises mobile and wearable electronic solutions that are otherwise difficult to achieve with conventional rigid electronic devices. Such solutions include printed functional electrical stimulation electrodes for patients with atrophied muscles. We also have applications that are more aesthetically inclined with the LED laces for shoes. We have the use of metallic threads to make ECG electrodes for heart rate monitoring. All these show us the possibilities of e-textiles and the applications that could emerge from it. However, both the textile and electronics have different mechanical properties. Textiles naturally lend themselves to washing and bending forces, and conventional electronics are usually enclosed in packages to limit their interaction with these mechanical forces. While flexible electronic devices exist, their bending range or twisting range is quite limited. Now, these mechanical differences poses reliability and integration challenges for e-textile manufacturing, both in the research domain and industrial domain. As we can see, the early attempts to integrate electronics into textile involved the use of portable devices that are placed into pockets. And these devices are very heavy and not suitable for long mobility applications. Now, improved versions include the printed and flexible ELM, where the rigid components of the electronics have been completely removed from the fabric. This enables the fabric to be more flexible. The integration technologies that have enabled e-textile over more than a decade now include the use of metallic copper wires, which are woven into the fabric as interconnections, and metal threads are also embroidered to make devices such as antennas or coils. And we have the use of conductive fabrics, which are heat laminated onto standard fabrics to make devices. Printing is also an approach for making electronics into the textile, and stretchable interconnects from the stellar projects have also been used These use the flexible circuits into conductors, and a more extensive approach of this is recently from the FED project, where standalone electronic devices on flexible films are woven into the textile. Now, all these technologies enable the integration of electronics into textile. Perhaps in the future, e-textile will be developed based on an interplay of all these technologies. At the moment, the printing solution, printed e-textiles, offer a single process for e-textile manufacture. Other approaches have sub-stages of integration, unlike the printing technique. So electronics can be easily transferred or localized on the surface of textiles with printed integration. Now, common processes include screen printing and inkjet printing. Screen printing enables roll-to-roll production of textiles in the textile industry. One of the challenges with printing on textile is the textile surface. The textile surface is quite rough, and to print conductors directly on the textile often leads to poor electrical continuity and high resistance. Now, to compensate for the roughness of the textile, multiple layers of the conductors are usually printed, and the conductor thickness can go as high as 45 microns, as we can see in the first picture by the right, where the thickness of the conductor is quite comparable to the thickness of the fabric. Now, what this does is, since metallic conductors are quite expensive, it increases the cost of the conductor, and when at this thickness, the conductor flexibility also reduces. Now, the interface layer is often a way out. It comes between the conductor and the fabric. Its main purpose is to eliminate the surface roughness of the fabric, thereby improving the electrical conductivity of the printed layer. And this also allows thicknesses of less than 5 microns to be printed on the textile, as we can see in the second picture by the right. The state-of-the-art interface layer was demonstrated on the polyester cotton fabric, and a thickness of up to 200 microns was achieved. At this thickness, the surface roughness of the fabric reduced to 3 microns. The figure on the right shows a comparison between the fabric surface roughness and the surface roughness achieved after the interface layer has been printed. This is a significant improvement in the surface roughness. However, this interface layer, the thickness contributes to more than 50% of the overall thickness of the e-textile. This means that an e-textile wearer can become aware of the printed film, and the resulting e-textile can become stiff compared to the normal textile fabric. So it is important that the interface layer reduce so as to improve the wearability of printed e-textiles. In this work, we look at 5 different fabrics to investigate how the interface layer thickness can be reduced. Now, the key thing with the fabrics, as will be shown in the next slide, is that they have different composition of materials, and in some cases, those made at the University of Southampton, the thread densities of the fabrics have been varied to see how this will affect the layer of the printed interface. Now, the interface layer printed is the Wearplex biomedical electrode. This was just used as a test to see how the interface layer can be optimized for such applications. Now, the UV curable polyurethane ink from Smart Fabrics was used to print the interface layer. And the number of layers printed for each of the fabric was optimized. And by optimization, we mean to achieve a surface roughness that is less than or equal to 3 microns, which currently represent the state of the art. Now, the fabrics made by the University of Southampton are in green in the table before us, and they have different thread count. Now, the thread counts here are given by the numbers just in front of the fabric. So the IsacordPoly 60, which means 60 thread per inch, 72 thread per inch, 80 threads per inch, and 88 thread per inch. And the number of prints for the first set of prints, 4 cycles of 4 printed layers was done. The second set of prints, you have less than 4 printed layers. Now, the results from the printing show that at high thickness of the interface, you have, and low thickness of the interface, the RA value is less than 3 microns for all the fabrics. And this is a very good result. It also shows that the surface roughness increases as the thread count of the fabric material increases. And for small increments in the thickness of the interface, the RA value is not significantly improved. This is because the screen printing itself has a tolerance of up to 50 microns when you're printing. Now, compared to the state of the art, the result here shows that the IsacordPoly was able to support an interface thickness of 50 microns, which is 4 times less than the state of the art. More importantly, at this thickness, the contribution of the interface layer to the overall thickness of the fabric is small, as shown in the second figure, here where we see the PU to fabric thickness ratio. Now, we also see that as the PU thickness increases, the thread count also increases. And one should be careful so that the PU thickness does not dominate the fabric as a Gaddamsilk fabric, where the PU is thicker than the fabric. At this point, the fabric basically becomes a plastic and not very wearable. Now, to conclude, we've seen that printed interface enable reliable and low-cost printing of conductive tracks on textile. By controlling the thread count of fabric, the printed interface can be reduced. A custom-made polyester fabric has been demonstrated to achieve 75% reduction in the state-of-the-art printed interface, while maintaining a good surface roughness. The benefit of this for e-textile manufacture is that it will reduce printing time, cost of ink, the electrical energy, and more importantly, the wearability of e-textiles. Thank you.